Let's see a few more examples now. The first one is the integral of x times the square root of 4x squared plus 1. And here, the natural thing to try is substitution, because this is not something that is an immediate antiderivative. Okay. Now, for a substitution here, there is a very natural candidate to try. Okay, because when we look at it, x times the square root of a big thing, it looks like the problem is this 4x squared plus 1 that is inside the square root. So if we want to write this simpler, that looks like the candidate for the substitution. So u equal 4x squared plus 1. So that du is 8x dx. Okay, with this information, we have here x square root of u, and then here we have du divided by well, let me write it. Dx is 1 over 8x du. So 1 over 8x du, the x's cancel out, and we get 1 over 8 integral of square root of u du, which is not a big deal. Okay, this one looks very easy. So this is 1 over 8 times 2/3 of u to the 3/2 plus c. Okay, just a power 1/2. And here we simplify a little bit. Well, we get this 1 over 12 u to the 3/2 plus c. But if we leave it like this, we would not be done. We need to substitute back 1 over 12 for x squared plus 1 to the power 3/2 plus c. And that is the final result for this integral. Again, please take a moment now to check that if you take the derivative of this function, you get the original function x square root of 4x squared plus 1. Let's do a few more examples. The integral of the cosine of 1 minus 3x. Okay, in this case, I think the substitution is very obvious. It's what is inside the cosine. So u equals 1 minus 3x. So du equals negative 3 dx. So this is the cosine of u times negative 1/3 du. And this is negative 1/3 integral of the cosine of u du, negative 1/3. Now we integrate sine of u plus c. Okay, and then remember, substitute back plus c. So negative 1/3 times the sine of 1 minus 3x plus c. Let's continue with the examples. X plus 1 divided by square root of x minus 2 dx. Okay, this one, again, here we see it has a quotient, but what really feels like a problem is that inside the square root we have x minus 2. So it's calling for a substitution. U equals x minus 2. Now let me be clear that you cannot be certain that the substitution is going to work until you try it and see that it works or not, okay? So be prepared to try a few things until one of them works. That's how it is. But in this case, this is the good one, I tell you. So let's do it. In this case, du equals dx. Okay, very simple. Here we have x plus 1 divided by square root of u du. And here we have a bit of a problem. You see what is happening? There are x's left. But x by the substitution is u plus 2. So we need to use that. U plus 2, then x plus 1 is u plus 3. And now we are good. Now we have all u's. Okay, so to compute this one is actually easy. We just break down the fraction. And we get two antiderivatives. This is the integral of the square root of u du plus 3. And if you want, you can write the integral of u to the negative 1/2. Okay, maybe it's easier to write both of them that way. So this is 3/2 u to the 2/3, sorry, the other way around. U to the 3/2 times 2/3 plus 3 times u to the 1/2 multiplied by 2 plus c. Okay, and then we need to substitute back, and we get 2/3 of x minus 2 to the 3/2 plus 6 square root of x minus 2 plus c. And now we are back to x's. Okay, and here you can see what I meant before with the example in the previous video. I gave example that the chain rule is like disassembling a watch and putting the pieces together in boxes, okay, in a neat way, but a way that doesn't let you identify how the watch looked like in the first place. Okay, so here we have this function, the antiderivative. When we apply the derivative and the chain rule and simplify, it becomes this x plus 1 divided by the square root of x minus 2. And then it's kind of difficult to connect the two of them, okay? At least by guessing. So it requires a bit of a process, this process of substitution. Let's finish with one last example. X sine of x squared divided by cosine of x squared dx. Okay, and this one is more complicated. I could have written it, this is meant to help. I could have written it like the tangent, x times the tangent of x squared. Okay, either way it will work. But it's probably easier. Well, let's do it like the tangent. Either way, the substitution is obvious here. U equals x squared, because that's what appears inside the trigonometric function, sine, cosine, or tangent. Du is 2x dx, and then this is the integral of tangent of u, and then x dx, you see it here, is 1/2 of the u. So this is 1/2 of the integral of the tangent of u du. This one we did in the previous video. Okay, so we can just repeat the computation here. I leave the computation for you. As in the previous video. We get negative 1/2. logarithm of the cosine of u plus c. Okay, and then we substitute back negative 1/2 logarithm of the cosine of x squared plus c. Okay, now just in case, let's do it the other way also. Let's start from the beginning and do it all the way until the end. The substitution is the same. Okay, u equals x squared, du equals 2x dx. So this is the integral of sine of u divided by cosine of u, and then dx is here. X dx, this x here and the dx here are 1/2 of the du. So this is 1/2 of the integral of the sine of u divided by cosine of u du. And here we would need to do a second substitution. Okay, so we call it v equal cosine of u. Okay. We may need to do several substitutions. dv is negative sine of u du. Okay, so we see the numerator sine of u du, that's negative dv. Okay, so negative dv divided by v. And this is 1/2, negative 1/2 of the logarithm of v plus c. And then we need to substitute back, okay, the logarithm of cosine of u plus c. And then we need to substitute back again the logarithm of cosine of x squared plus c. Okay, because we did two substitutions, we need to substitute back twice.